Hello, y'all. Welcome to my DP chemistry curriculum. Today we're going through lesson 95, reactivity 3.1.2 and 3. Reactivity 3.1.2 is talking about how a pair of species differing by a single proton is called a conjugate acid-base pair. So we'll deduce the formula of the conjugate acid or base of any Bronsted-Lowry base or acid. And 3.1.3 has how some species can act as both Bronsted-Lowry acids and bases. We'll interpret and formulate equations to show acid-base reactions of these species. We'll kind of be doing that throughout, and as well as we'll go over the name for these types of species. So without further ado, let's get started. One of the cool things to do is we'll use the reaction between ammonia, NH3, and water that we saw earlier in lesson 94. So when we look at ammonia, which we know is a Bronsted-Lowry base, the gas reacts with water to form in actually an equilibrium reaction, NH4 plus H2O. Or sorry, not H2O, OH minus. And that's our hydroxide. So we noticed before that water donates its proton H plus to solution to the ammonia, and therefore this is our base. It's accepting the proton, and this is our acid. It is donating the proton. So we've already learned about this. But the crazy thing is this is reversible. So if we look at the reverse reaction, and I'll highlight that in green, we now have ammonium, which will be giving its proton to hydroxide. So this is actually going to act as an acid, while our hydroxide is going to act as a base. And these are Bronsted-Lowry acids and bases. What that shows us is that we actually have what are called conjugate pairs. Conjugate pairs were what we described as two species differing by a proton. That was the definition, which remember, that's an H plus, a hydrogen ion. So we have one pair, ammonia and ammonium, and we have our second pair, water and hydroxide. So those are our two conjugate base pairs. Oops, got that one wrong. This is or just conjugate pair. Conjugate pair, as well as these two. Conjugate pair. So we can do another example. So we can look at the reaction of HCl plus water. Whoops, that's going to be a liquid. These become now hydronium, as we saw the acids become in water. And we get Cl. So as we react these, or chloride, as we react these, we notice, once again, our hydrogen was donated and our water accepted that hydrogen. While this reaction we'll find later is not technically reversible, if we were to look at the reverse reaction, so once again, we'll look at the reverse, we'll find that water is now donating the H plus and chloride is accepting it, meaning water will act, or hydronium will act as the acid and chloride will act as the base. So we can have these working both ways. In our first example, NH3 and NH4 plus are conjugate pairs. Generally, we'll refer to the first one as our base and the second one as our conjugate acid. We'll usually refer to the product as the conjugate. And then in our second one, HCl and Cl minus, this will be our acid, with our chloride being our conjugate base. So that's kind of conjugate acids and bases and conjugate pairs. But there's a weird thing that you may have noticed. We also have something called amphiprotic species. Amphiprotic species is a species that can act both as a Bronsted-Lowry acid or base. Now you notice that in our second reaction, water was our base, but in our first reaction, water was our acid. Water is a great example of this. Because water as H2O can either add an H plus and become hydronium, and therefore it is receiving the hydrogen, or it can remove an H and become hydroxide, donating the hydrogen. And so water can go either path. It can become the hydroxide ion, or it can become the hydronium ion. Other very common examples of these amphiprotic species are going to be hydrogen carbonate, CHCO3 minus, hydrogen sulfate, SO4 minus. We could have hydrogen H2PO4 minus, or even HPO4 not 3 minus, 2 minus. The very similar thing that you can find out about all of these species is that it must be able to both accept or donate a hydrogen. And so pretty much any di or triprotic species that is missing one hydrogen, but still has one to donate, usually will be amphiteric. Amphiprotic. So something like hydrogen carbonate comes from H2CO3, carbonic acid, a diprotic acid. Hydrogen sulfate comes from H2SO4, or sulfuric acid. Dihydrogen phosphate or hydrogen phosphate both come from H3PO4, phosphoric acid. So you'll notice they're acids that are already di or triprotic and have lost one hydrogen, yet still have another to provide. So those make great amphiprotic substances. Anyways, I hope this helps and have a great day.